In this video, we are going to go over the ideal gas law lab. Now, this is the actual lecture that I would give in class, but you can read it when you're doing homework in the middle of the night like most students do. So let's just start with some of the earliest experiments in chemistry and physics involve the study of gases. The invention of the barometer and the improved thermometers in the 17th century permitted the measurement of macroscopic properties such as temperature, pressure, and volume. Now, scientific laws were developed to behave under certain conditions, but an explanation or model of how gases operate on a microscopic level was yet to be discovered. These laws allowed the prediction of how gases behave under certain conditions, but again, an explanation or a model of how gases operate on a microscopic level was yet to be discovered. After Dalton's atomic theory, and what the atomic theory states is that matter is composed of atoms. Now, after that theory was proposed in the early 1800s, a framework for visualizing the motion of these particles followed after that. The kinetic molecular theory developed by Maxwell and Boltzmann in the mid-19th century described gas molecules in constant random motion. Molecules collide, resulting in velocities. Now, these collisions exert pressure against the container walls, and the frequency of collisions and the speed of distribution of these molecules, they depend on the temperature and the volume of the container. Now, because of that, the pressure of a gas is affected by changes in temperature and volume. The simple experiments that follow opportunity to play the role of a 17th century scientist with some 21st century tools, where you're going to discover the laws all for yourself. Laws and constants that are still in use today. Now, liquids contain molecules that have different kinetic energies due to different velocities. Some faster liquid molecules have enough kinetic energy to vaporize, and some of the slower vapor molecules condense into liquid. In an open container, the rate of vaporization will be greater than the rate of condensation, and the liquid is eventually going to evaporate. But in a sealed flask, there will be a point in which an equilibrium is reached between the rate of vaporization and the rate of condensation. Now, to the eye, it seems that the liquid doesn't change at equilibrium, but the microscopic level, a vapor molecule enters the liquid phase for every liquid molecule that enters the gas phase. So I show you some of these so you can see them, and when we go talk about them, you're going to have an idea of what you're looking at. The main theory states that there are several variables that cause the behavior of gases. They're going to be volume, represented by that capital V. They're going to be temperature, represented by that capital T. It's going to be pressure, represented by that capital P. And then your amount of your gas, which is that lowercase n. Now, because gases follow those patterns, it's assumed that gases behave, quote unquote, ideally independent from the composition of the gas. Now, this is why we call it the ideal gas law. The ideal gas law also includes the ideal gas constant, which is your R, and that's shown here. R equals 8.31 liters ATM, or atmosphere, over moles Kelvin. These are things you need to make sure you're familiarizing yourself with as this lab goes on. This is the ideal gas law equation. As with all equations, it can be rearranged so the ideal gas constant is on one side of the equation all by itself. So that's what we have on your upper right, that's your equation, and on your lower right is going to be our rearrangement. And just notice on the left-hand side of the screen, all that is telling you what each letter represents. So hopefully you can take this information and get through any problems that you're having on your lab homework. So now when metals are reactive, there we go. When metals are reactive with aqueous acids to produce hydrogen gas and metal salt, a metal oxidizes by losing one of their outer shells of electrons. What do we have? When we say oxidizing, we're talking about rust. This reaction forms monoatomic cations, while the hydrogen cations from the acid are reduced by gaining an electron to form elemental diatomic hydrogen gas. Now remember that in this reaction, when acid is in excess and is completed with no side reactions, an assumption is made that the number of moles of gas produced can be predicted from the mass of the metal according to the stoichiometry equation for the reaction. The assumption also says that the gas can be collected and its volume determined under measured conditions of pressure and temperature. Now, that information is how you can determine a value for the gas constant, which is represented by R. In this procedure, you're going to be using a magnesium strip and a eudiometer to collect the hydrogen evolved. The gas bubble formed after the expansion will collect and be trapped in the eudiometer within the glass walls and the water remaining in the tube. Once you submerge the eudiometer into the equalization chamber up to the point where the water level in the chamber is level with the water level in the eudiometer, the pressure of the gases inside the eudiometer, which is going to be your P total, is going to be equal to the external atmospheric pressure, or your P bar. So P total is going to equal P bar. Now, since the hydrogen gas is collected over water, the total gas pressure in the bubble, or your P total, will be from the H2 produced in the chemical reaction and partially due to the pressure water of vapor, which is your pH2O. To determine the pressure of the hydrogen gas, which is your pH2, the vapor pressure of water must be subtracted from the atmospheric pressure, which is your ATM, and you're going to read that from the barometer on your on the desk in the actual lab. Just keep in mind that if you're struggling or you have questions, you have many tools in D2L. You can reach out to your instructor. Make sure you reach out to us, everyone. We're all here to help you. So if you're struggling, make sure you reach out. And I hope this video is helping you out a little bit.